Well, hey, it's Dr. J. I'm back with some more Riemann sums, continued. In this lesson, we're going to learn about the midpoint method. It's very similar to the left and the right endpoints that we talked about in the last video, but in this one, instead of going to the left or the right of the rectangle, we'll shoot straight down the middle. And if we have a curve, say y equals f of x, and we start at A, and we end at B, and we divide it into n rectangles, so n is the number of rectangles. Instead of taking the point on the left or the right, we will take a rectangle. And when I first learned this, I thought, well, the midpoint seems like the one we should have done first, right? Because it seems more natural to sort of take the average, right? The left, you might notice if you did some of these homework problems on the left side or the right side, you're either getting an overestimate or an underestimate. But the midpoint kind of handles that by taking the point that's directly in the middle of the interval. So remember, delta x is the width of each rectangle. So the width of each rectangle is the same. We call that delta x. Let me say width. That's how wide this rectangle is here. To find the point right in the middle, we'll call this A1. A1 is delta x, the width, times f, the function value, in other words, the y value here, of the point that's exactly in the middle of this interval, which will be A plus 1/2 of delta x. That would be your area for A1. And then for A2, again, take the midpoint and have that be the roof or the roof. Yeah, right down the middle. That's your A2. Right down the middle. And again, this has the same width, delta x. Now think about this for a minute. To get to the middle of the first rectangle, you add half of a delta x. So to get to the middle of the next one, you add 3/2 of delta x. You see that? I don't know if it's clear by the diagram, but so this is a half. That's half of delta x. It's red is 1/2 of delta x. This little line right there. And then you've got another half. So that's 2/2, and then you've got another half. So altogether, that would be 3/2 of delta x. Or if you prefer decimals, 1.5. I usually write it as a fraction initially, and I'll use a calculator in decimals if necessary. And then I'll just say, etc., etc., etc. We'll go the middle of each one of these intervals, and we will create a particular number of rectangles. How many did I just draw? 5? Let's do 5. So let's do one to get the ball rolling here now that we've sort of refreshed the memory of the formula with this new add-on here that we're now taking the point in the middle of every rectangle. All right. I'm going to go ahead and call this example 6. Because after a short break, came right back. This is not really a new lesson. This is just a continuation. So I don't normally do this, but you're seeing this in real time here. So we just continue right where we left off. So example 6, find the area or find the approximation of the area under the curve e to the negative x on the interval -3 to 1 using n equals 5 and the midpoint method. Or I've sometimes heard it called the midpoint rule. Okay, just a quick, very quick graph without even using graph paper. If you haven't seen this function in a while, it's the natural exponential with a negative power. So it has a y-intercept at 1. Y equals 1. If you plug in 0, you get out 1. We're going to go from -3 to +1 on the x-axis. That's our A and our B. And the function, because of the negative power, goes up to the left and down to the right like that. It should be smooth curve like that. All right. And then this point right here is 1. We're not going to use that point because it's not a midpoint anyway. So we want to know this area here under the curve. Now we're using 5 rectangles. So our delta x, just a quick reminder, watching this video on a different day than I filmed it, b minus a over n. So b is 1, a is -3, and n is 5. So 1 minus -3. Be careful, that's 1 plus 3. That's 4/5. That's going to be the width of each rectangle. So I got to do 5 rectangles. 1, 2, 3, 4, and 5. And they're a little bit off of the integers because we have 5 rectangles and the size of the interval is 4, right? So the distance from -3 to +1 is only 4. And so you can kind of verify that your delta x makes sense. You know, the size of the interval is 4 units from -3 to 1, and we're dividing it by 5. So this point right here will be the first midpoint. So we've got A1. That'll be our first area. Will be delta x times f of A plus 1/2 delta x. In fact, this formula, we could just keep repeating it. We just changed the fraction here from 1/2 to 3/2, so on and so forth. All right. So we're going to do delta x is 4/5. F of A is -3 plus 1/2 of delta x. So 1/2 of 4/5. So our A1 will be 4/5 times f of negative 3 plus 2/5. If I could squeeze that in here, 4/5 f of, I mean, I guess I could write it as a mixed number, but I'm not going to. Here, let's just do a quick fraction here. This would be, here, let's do it as a decimal. 2/5 is 0.4. Half of 4/5. I usually don't go with decimals so early, but I'm making an exception because this is a very nice decimal. 4/5 is 0.8. So half of 4/5 is half of 0.8. Half of 0.8 is 0.4. It just makes it a lot easier than trying to use mixed numbers here. So this will be negative 2.6. So that'll be our A1. I better start documenting all of this. I don't want to get rid of that. So A1 is 4/5, which is 0.8, times f of negative 2.6. I will use this function in a minute. I'm going to go ahead and wait. So let's save that. We'll wait and come back to that. If you want to do it now, you could just take negative 2.6, plug it in here for x, and that would finish off A1. I'm going to just stack them up like I did last time. All right, A2. So A2. So we want the middle of the second rectangle. The middle of the second rectangle. Just change this to a 2. A2, A2, and change 1/2 to 3/2. So again, 1/2 gets you to here, gets you halfway through A1. Another half would get you right there. That would be an endpoint, a left endpoint. You want to go to the middle. So that's 1, 2, 3/2. 1, 2, 3/2 gets you to here. I better doctor a lot of this up, so I'm trying not to reproduce my results. So 3/2 of 4/5 is 1.2. If you don't believe me, put it in your calculator. 3/2 is 1.5. 4/5, we already said, is 0.8. And 1.5 times 0.8 is 1.2. So my A2 will be 0.8. That's my delta x. And then f of negative 3 plus 1.2, which would be negative 1.8. And we only have 3 more to go. All right, next one, A3. So again, you're essentially adding 2 halves to each interval in order to get to the midpoint to find the roof of that rectangle. So A3, I'm intentionally reproducing it each time using the same recipe. So that would be 5/2. 5/2. 5/2 is 2.5. 4/5 is 0.8. 2.5, that would be 2. Yeah. 0.8 times 2.5 just comes out to be 2. So that was nice. A3 is 0.8 times f of negative 1 because it's negative 3 plus 2. All right. I do have my calculator right here if we need it. I'm trying to avoid it until it becomes necessary. That's kind of nice. So this midpoint right here is in fact negative 1. Yeah, that's f of negative 1. I could label all of these. Why don't I do that for you while we're sort of just digesting what I just said? So this midpoint is negative 2.6, and then I plug it in to find the roof. The next midpoint is negative 1.8, and then I plug it in to find the roof. Notice I'm waiting to plug it in until I've got them all lined up. You could plug them in as you go. The next midpoint is exactly at negative 1. You might start noticing a pattern where you could skip a lot of this work. You want to take a guess at where the next one is? Negative 0.2. Right? Notice it's just going half. Well, actually, I shouldn't be guessing. I don't want to guess without drawing the picture. So I'm going, here's A2, oh, sorry, A4. What am I up to? A4. I'm halfway. Yeah. So it is negative 0.2. Negative 0.2. The y-axis is sort of getting in the way here. Yeah. There's your y-axis is right there. Maybe I'll draw it like a very ghostly y-axis. There's my y-axis. So none of the endpoints or midpoints are right on the axis, so it's kind of in the way there. It's cutting across right there. And then finally, A5. Again, you could probably just guess. You're going to go 2 more halves. So you're adding another delta x. So that's going to put you at 0.6. So A5 is 0.8 times f of positive 0.6. And those are your 5 rectangles, and then we're going to add them all up to approximate the area. So this pattern that's generated by this formula here, after 2 or 3 or 4 or however many rectangles it takes, some people can see the pattern after just 2. It usually takes me at least 3 to start to notice the pattern. See? Negative 2.6, and then it went to negative 1.8, then it went to negative 1. So each time the next midpoint is exactly a delta x away from the one prior to it. Now you're going to need your calculator because you can't very easily calculate exponential e functions without it. You do have an E button on your calculator, so get your calculator of your choice out. I'm going to try the phone again. So we got negative 2.6. Now I want to point something out. The function is already negative. So when you plug in negative 2.6, it's going to be double negative. Negative, negative. So you might as well save yourself a step and just plug in positive 2.6. Then hit your E button. So that's your E. That's the roof. That's where the roof of the first rectangle is. It's the Y value. And why don't we just knock it out so I don't have to waste a lot of space here. Multiply that by 0.8. I'll just do 4 decimals for now, and then I'll round. Probably just round to 1 decimal when I'm done. It's usually 1 or 2. But to be safe, I always keep at least 4. And then before, submitting, make sure you read it carefully. Now, I'm doing that. I'm multiplying it now because I've already got it on my calculator. You've seen the other technique, which is where you could wait on the delta x. You could do all the function values, right? Add them up first, and then multiply them all by, multiply the result by 0.8. Either way, I recommend you try it both ways to see. This way seems to be easier since I already have it written out here. So I'm just using what I've got. All right, so let's do the next one. F of negative 1.8. Again, that's a double negative. So when I put it into my calculator, I'm just going to put positive 1.8. And then I'm going to hit E. Right? And again, I don't want to write that down twice. So I've got it already in my calculator. Now I'm going to multiply it by by 0.8. So that's 4.8397. And so on and so forth. Some of these you could do with mental math. Maybe this one we could do with mental math. So what would that be? That would just be E, right? Because if you put a negative 1 into a negative x, it's just going to come out e to the 1. So there's E. Remember E? We learned about that a while ago. You should probably have that memorized. And then times 0.8. That's about the only one that you can do from memory. Although you memory and a calculator. The calculator is like your memory assistant. So here we have negative 0.2. Again, double negative. So it's going to change to a positive. All right, double negative changes to a positive. So 0.2 on my calculator. E. That gives me 1.22, so on and so forth, times 0.8 is 0.9771. And then the only one that I actually use a negative power is the positive one. That's this last one down here, A5, right? That's 0.6, so that's actually going to stay e to the negative 0.6. That one does not change to positive. Although you will notice that when you take a negative power of an exponential, you do not actually get a negative number. It's still above the axis. We'll talk later, not in this video, but in a future video about what a negative area would mean. That's a topic for another lesson. I would say in these first, introductory sections on the Riemann sums, all the areas are positive. And again, we'll get into that later, but for now, if you get any negative numbers here, you definitely did something wrong, because we're adding up a bunch of positive numbers. We're above the x-axis. At some point, if we go below the x-axis, that could possibly change, and we'll have to handle that separately. Now, since I already multiplied by 0.8, I'm just going to go ahead and add all these up. All right. And this is what's called sigma notation. I'll start using that now. It's a fancy way to say add a bunch of numbers together. I didn't give myself enough room. I'll write it over here. Sigma notation. A1 plus A2 plus A3 plus A4 plus A5 is equal to sigma. Sigma is the capital Greek letter S. Yeah, it means sum. From 1 to 5. So we say sum from 1 to 5. We start at 1 to 5. I is called the index. So we use the letter I. So this is I equals 1. This is I equals 2. This is I equals 3. This is I equals 4. and this is I equals 5. So we're adding up 5 areas. So we say AI, and then you put it into your calculator and add them up. I'm going back to traditional calculator here. So 10.7709 plus 4.8397 plus 2.1746 plus 0.9771 plus 0.4390. And if I didn't hit any buttons incorrectly, that should be the correct sum. 19.2 rounded to the nearest tenth, or as directed by the problem. When in doubt, do 4 decimal places, and then you could always back up if you need less. If you don't have enough decimal places and you find out you needed them, you're going to have to start all over again. That's a real bummer. It's better to overestimate, and then you could always back up if you need to. All right, so that is your midpoint rule and a very brief introduction to sigma notation, which I will summarize in the next example. All right, so to summarize the Riemann sums, we are approximating the area under a curve. It's a function y equals f of x on the interval AB using n rectangles, also known as subdivisions. Or subintervals. So we're going to divide this interval up into n little pieces, yeah, or n rectangles. And so we've learned 3 different methods, and we can start them all the same way. Yeah, so the area is approximately the sum. So that's a Greek letter S. We read that as the sum from I equals 1. I is called the index to n of the area of each rectangle, which is the width, delta x, times, now you can omit the dot, I usually do, times the function value at xi. And so all 3 methods use the same basic setup, where delta x is the width of each rectangle, so b minus a divided by n. And so from what we've learned before, I is the index. Each one of these is an area. So I was calling these A1, A2, A3, etc. So that's AI. So essentially what this means, sorry about that, the index ranges from 1 to n, and so that creates a sum A1, that's when you start at 1, and then you go to A2, and then I'm just going to say dot, 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 A3, A4, A5, however many rectangles you have, and then you stop at the last rectangle, AN. So this notation is a way of writing this sum in a more condensed form that applies to all 3 methods, the right hand, the left hand, and the midpoint. So the only thing that changes is xi. Xi depends on the method. So which method are we using? Well, there's three different methods. Yeah. The easiest one by far is the right-hand method, or the right endpoint. That's my personal favorite, because xi is just starting at a, whatever the a is on your interval, plus whatever I is. So it just ranges from 1 to 2 to 3 to 4, all the way to whatever the last rectangle is, and then multiplied by this delta x, which you compute at the beginning of the process. That is the one that I personally just memorize, and you could carry that with you. It's very compact. The other two get a little trickier. They get a little bit trickier. The left endpoint is the one we actually started with. We went from left to right to middle, but then when I memorize them, I go from right to left to middle. The left endpoint is the same formula as the right, minus you're shifting that endpoint, which used to be, I don't know if this is going to be helpful, but just like a little diagram here of a rectangle. The right endpoint is in the right corner of the rectangle. The left endpoint, you just shift this. Oh, I got off the screen there. You just shift this point to the left so that it appears here at the top left corner of the same rectangle. So all of your right endpoints just get shifted to the left by exactly 1 delta x. So you say I delta x minus 1 delta x. And that's how you get the left endpoint. Now remember, the width of each rectangle is the same, so they're all delta x's. This one can be simplified. A plus, you can combine the delta x's by factoring I minus 1 delta x. Which essentially means when you plug in 1 for the first rectangle, this would then become 0, this factor here. When you plug in 2, this factor would become 1. So basically the index is shifting over from the right corner over to the left corner. Okay. That's how I think of it. I actually think of the dot as actually sliding over to the left. And then the one we just did, the midpoint rule. Let's hope I can squeeze this in here. This one's a little trickier now because you're going in the middle. So it's a plus I delta x, but now you're putting your dot right in the middle, right in the middle of the rectangle. So you're going to subtract half of a delta x. By putting the dot right in the middle, that's half of a delta x. Essentially halfway across the top of the rectangle. I'm trying to fit it on the screen there. I don't know if I'm making it worse or better. There we go. I think that fits. There you go. Barely. Okay. Now you could just leave it like this, or you could simplify it. I don't have much space, so I'm going to combine all this together. It's 2I minus 1 over 2 times delta x. There's a little bit of algebra that goes on here. You have to multiply the middle term here by 2 so that you can combine these terms together. Then you get 2I minus 1 all divided by 2, and then you only have to write the delta x one time. So those are your 3 methods for Riemann sums to approximate the area. So let's practice these. And it's really going to be important to, follow the method that's suggested and then know these formulas. So I would write these down. It's all one formula to begin with, but then depending on which method you're using will determine which of these xi's you're going to use. And then we'll get deeper into the techniques for handling the I as the index moves along, starting at 1 and going to whatever n is. Okay. So example 7. Find the area or approximate the area under the curve f of x on the intervals 0 to 3 using 4 rectangles. And let's start with right-hand endpoints. So that's the easier one, right endpoints. I'll do the other two as well, but not on this particular example. Oh, and I got to give you an f, so I have a pre-prepared f here. So you don't have to sit here and watch me graph it. So this is our function f of x. It's a exponential function. It's a little bit more exotic than the last one we saw. It's got this little hump in it. And we're going to use 4 rectangles on the interval from 0 to 3. So we're going from 0 to 3, 4 rectangles. So the first thing we should do is figure out what delta x is. That's going to be b minus a over n. So each rectangle has a width of 3/4. And we're using right-hand endpoints. So there's 3/4. All right, now let's watch how the formula works. So x1, once we have the delta x, we can find our x1. Well, it's definitely going to be 3/4 because that's your first rectangle, right? There's your first rectangle. It looks like it's hitting at 3, but it's a little bit above 3. It's like 3 point something. We'll figure out exactly what that y value is in a minute. Because it's this e to the x thing, it's going to have decimals in it. But let's focus on the x's first. So x1 is 3/4. You could just write that right now, right? But remember, I want to show you the formula. So xi is a plus I delta x. So that means x1 is 0, yeah, because a is 0, plus I is 1. Yeah, the index is just whatever I is. And then delta x, sometimes I omit the dot, but in this case I'm going to write it. It's 1 times 3/4. Or you can use parentheses. Parentheses might be a little better. 1 times 3/4. And I hope you can see clearly without using a calculator, that's pretty clearly 3/4. Right? 1 times 3/4 plus 0 is 3/4. So that's your x1. All right. Now you can just try to figure out what x2 is. All right, there's x2. If you know what that is, that's great. Write it down now. If you don't, use the formula. So x2 is 0 plus 2 times 3/4, which is 3/2. Yeah, or 6/4, same thing. So here you go. x2 is 3/2, also known as 1.5. Let me write these a little bigger so you can see. So 3/4, that's my x1. There's my x2. And keep going. Well, let's draw this rectangle. There's my second rectangle. All right, and here's the next one. X3. X3, can I fit it in here? Oh, squeeze it down here. X3 is 0 plus 3 times 3/4, which is 9/4. Did that fit on the screen? Barely, 9/4. So that's 9/4. Also known as 2.25. You can see on the graph, it's just a quarter past 2. All right. And then there's a bunch of things I like about the right-hand method. It's easy to memorize. Most people are right-handed. 90% of humans are right-handed, so it seems more natural. And also, the last thing that I love about it is X4 is always the last endpoint. The right endpoint. It's always B. And that's a nice little fact that's always true. So the B is 3, so that means the last right-hand endpoint must be B. Yeah, it's the last point on the right, so that's the one you're going to get for free. Again, I call that a freebie. Yeah, you don't have to solve for the last one. So that's the advantage of the right-hand endpoint rule. All right. Now you're not done yet. You got to find the y values now. So to find the y values, that's f of x1, f of x2. Oh, we got to get that in there. Let's just call them f of xi, and it depends on how many i's you have. We've got 4 i's, so I equals 1, 2, 3, and 4. So that's going to be the y values of these 4 points here. And you use the given function to find what I call the roof of the rectangle. So f of x1 is 6 times x1, which is 3/4, times e to the negative 3/4 plus 1. So that'll be this first roof. It looks like it's about 3. You got several ways to do this. Let's do the phone calculator. So first, let's do the e. So we got 3/4. I'm just going to write that as 0.75 negative. Or I could have divided 3 divided by 4. And then e. So that's the e part. And then, how should we do this? Let's do 6 times 3 is 18. So let's multiply that by 18. I'm just kind of doing it all mentally here. 6 times 3 is 18. So that's now multiplied by 18 and then divided by 4. Another way to do it is you could turn this into a decimal. That would be 18/4, which is 4.5. Right here, I have my other calculator to back me up here. 18 divided by 4. Yeah. So I could just write that as 4.5 and then e to the negative 0.75 plus 1. I've already put it into my calculator, so here we are. Come on, phone, turn back on. There we go. So that's just these first 2 terms, and then plus 1 is 3.1256, blah, 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 blah. It's better to keep more decimals than less. All right, so let's do the next one. I don't need any of this anymore. So let's do f of x2. So 6 times x2 was 3/2. I know I'm offline a little bit here, but x2 was 3/2. So 6 times 3/2. Or you could say 1.5 e to the negative 3/2 and then plus 1. 6 times 3/2 is 9. E to the negative 1.5 plus 1. 6 times 3 is 18, divided by 2 is 9. Multiplying and dividing, you can be pretty, you can be creative about how you do the order of operations. What you can't be creative about is the exponential must be done first. Right? That's the order of operations you learned as a kid. Exponents go first. So you get e to the negative 1.5 is a decimal. Yeah, that's just this part. And then times 9. And then plus 1. So this is going to be 3.0081. Yeah. So my graph's a little off. Yeah. I wasn't being very precise with the graph. It's a little flatter here. I'm not going to fix the graph, but this dot here should have been a little bit closer to 3, and then this dot should have been a little bit above 3. But again, the graph is just an assistant. It's not solving the problem for you or anything like that. All right, f of x3. So x3 is 9/4. So we got 6 times 9/4 e to the negative 9/4 plus 1. 6 times 9 is 54. 54 divided by 4 is 13.5. So it's 13.5 e to the negative 2.25 plus 1. So 2.25 negative, and then do e, and then multiply by 13.5, and then plus 1. So that's 2.4228. Again, my graph's a little bit off. This dot should have been a little bit higher. One trick, I know it doesn't really matter, but you could just do something like this and just say not to scale. Right? And so the y values are not to scale. They're just there as to give you a visual, something to look at while you're doing the problem. All right, so there's your x3, or your f of x3. And then the easiest one is actually the last one, because the last one, x4, is just the right-hand endpoint. So f of x4 is 6 times 3 e to the negative 3 plus 1. Just plugging in the right-hand endpoint. So that's 18 e to the negative 3 plus 1. So negative 3, and then e. That's e to the negative 3, and then times 18. Yeah, and then plus 1. So that's approximately 1.8961, blah, 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 blah. Okay. All right, so let's write all these down now. We already have them written down, but let's write them down nicely. So we've got fx1 times delta x. Here, let's do it this way. A1 is delta x fx1, which is 3/4, which is 0.75, times, so 0.75 is the delta x, that's the 3/4. It's easy to forget that by the time you get this deep into the problem. Go back, pick up your delta x. You can either write it as a decimal or a fraction, and then this is your f value, 3.1256. That's enough decimals. And then we've got a2, delta x, f of x2. That was 1.5. No, sorry. The x2 is 1.5. That's true. But the delta x is always the same. It's 0.75. And then the f of x2 is the number that changes, 3.0081. And then your a3, delta x, f of x3. Again, keep the delta x the same. And then multiply by the f here, f of x3, 2.4228. And then your a4, delta x, f of x4 is again 0.75. And then this is your f of x4. That was the last one I did, 1.8961. And then you're going to add these up. So the area is approximately A1 plus A2. Let me just write it with sigma notation. The sum from I equals 1 to n of AI, all right, which is just adding up all of these numbers. Now you have a choice. You can multiply and then add, or you can add the f's and then multiply by the delta x. I'm actually going to do that. I'm going to do 0.75 times, and then I'm going to add all the f's. So I can add all these function values. Yeah. They're really the y values. Yeah, or the roof of the functions. And then multiply. You only have to multiply once. And for this, I like to use old-fashioned calculator because I don't want to hit something wrong. So I've got 3.1256 plus 3.0081 plus 2.4228 plus 1.8961. So when I add up all those values, I get 10.4526. I'm using brackets. They mean the same thing as parentheses. You know that. And then multiply that times 0.75, and you get 7.83945. You may round to the nearest hundredth in this one. So 7.84. And that would be my approximate area under this curve here. So that's the final area. That's the Riemann sum, or the right-hand approximation using 4 rectangles. I want to show you the left hand and the midpoint again. I know we've only seen the midpoint once, so we'll see that again. But the right-hand one is the one we're going to use the most moving forward, so I've really put a lot of time and effort into this one. Now, what I want to show you next is how to do this. Tips for adding using I. All right, so I got a few more examples of not actually particular area functions, but just some tips, if you haven't seen this before, for adding up a bunch of numbers very quickly. Because I don't know if you are catching on to this. I've only used, 4 or 5. I think I did 6 rectangles at one point. But this can be tedious, right? And I mean, what if you really wanted to do a good approximation, right? To do a good approximation, I mean, this is pretty bad. It's not, I mean, It's not very close to the actual area, right? If you want to get close to the actual area, you need to use like 100 rectangles, right? Maybe not 100, but 12 or 20 or something like that. A lot more than 4. And you can imagine if I were to do this problem with 20 rectangles, we would be here for a long time hacking away on the calculator to try to get it. So some tips for adding. So I'm not going to call this an example quite yet, but let me just show you some tips. One of them you learned as a young child. Suppose you wanted to add from 1 to 20 a constant, like k. Sometimes I use c for a constant. This time I'm using k. So just think of a number, 5 or something like that. In fact, let's do it. Let's just do 5. Because this has no I, right? There's no index I. That's what makes it a constant. So a constant is a number that has no index. Well, what does this mean? This means 5 plus 5 plus 5 plus 5 20 times. You learned this in like 3rd grade, probably 2nd grade. That was back when math was easy, right? 5 plus 5 plus 5 plus 5 plus 5. Your teacher says, I want you to add up 5 plus 5 plus 5, and I want you to do it 20 times. That's just 5 times 20. Or in a parenthetical notation, 5 parentheses 20, which is 100. So what does that tell us? That tells us if I have to add up a constant, the same constant over and over and over again, I don't actually have to add them, right? That's one of the oldest tips you learned as a child, right? You can just multiply by however many the index is. Not the index, the n, top of the sum. Right? The index tells you as you're counting along, but then you stop when you get to the last index, which is the top 20. So that means no matter what the constant is, if you add from 1 to n, doesn't have to be 20, it's just going to be k times n. Or you could use an x if you like. It's pretty dangerous because there might be x's in the problem, so either use a dot or parentheses or something like that. All right, so that's your number 1 tip. All right, let's save that up here. I equals 1 to n of a constant is just k times n. That's our number 1 tip. All right, number 2. Suppose I wanted to add from 1 to 100 the index I. So this is the index. It's not a constant. Yeah, it's like a variable, But it's a variable, and the reason why we call it the index is because it's a variable that changes according to a pattern, right? It's not a random variable. It starts with 1, and then it goes to 2, then it goes to 3, 4, 5, 6, 7, 8, 9, and then it goes to 99, and then 100, and then it stops. Now, I don't know about what your experience was, but this is probably more like, I don't know, 4th grade or something, right? If your teacher was, trying to keep you busy for a little while, a teacher, good elementary school teacher will tell the students to add up 1 plus 2 plus 3 plus 4 plus 5. And sometimes I might even put you into groups and let you, divide up the labor a little bit. But, I know I had a teacher that had us do that. And there's always a trick. Yeah. And the trick is you don't actually have to add them all up. You take the last number, you multiply it by the last number plus 1, and then you divide by 2. I don't know if you remember this, but this was a trick or a technique. Yeah. And the reason is, look, 101. Yeah. 99 and 2. Well, guess what? That's also 101. Yeah. And then the next number before that one was 98. 98 and 3. That's also 101. Yeah. So you essentially have 50 pairs of 101. 50 pairs of 101. It just keeps going like this until you get down to the last pair. The last pair will be 50 and 51. Yeah. And so all you have to do is multiply 50 times 101. And the answer is 50/50. Now, you could actually go 1 plus 2 plus 3. Try it. Someday try it. Actually, sit there on your calculator and go 1 plus 2 plus 3 plus 4 plus 5. If you've got some time to kill, go ahead and do it, and you'll see, oh, yeah, Dr. Jordan's right. It's just 50/50. All right. So what's the tip for this one? Well, the tip is it doesn't have to be 100. It could be n. So n would be the last number. Then you do plus 1, and then you do divided by 2. So the next tip is the sum from I equals 1 to n of the index, just the index, is n, the last number, times one more than that number, n plus 1, all divided by 2. All right, so that's tip number 2. All right. This is going to help us immensely with problems that have lots of rectangles. Yeah, it's going to give us a quick way. I mean, I just added up 100 numbers in like a second or 2 seconds, right? And all right, so the next one's a little bit less intuitive. Rule number 3 or tip number 3 would be if we were adding up from I equals 1 to n perfect squares, I squared. So this would be something like 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, etc., and then stopping at n squared. I'm going to erase those. We don't need those anymore. Right? This one's a little bit less intuitive, so I just memorized this. If you can, or just write it down and keep it handy. All right. These two, I can walk around. I've been doing this for 30 years, and these two just can be memorized like basic number facts that you memorized when you were a kid. But this one is a little bit less easy to memorize. It's n times n plus 1, so it starts off easy, and then it goes 2n plus 1 divided by 6. So that's your summation formula for adding up squares. If you just want to get the idea of how it works, try a really easy one, like from I equals 1 to 4 of I squared. So that would be 1 squared plus 2 squared plus 3 squared plus 4 squared. So we want to memorize a formula, memorize it. That's good. I mean, I totally respect that, and I do it all the time. But then if you want to really kind of have a feeling for why that formula is true, so you're not just memorizing some random fact that doesn't seem to be true, just check it really quickly. And if with a small one, you can just do it, right? 2 squared is 4, 3 squared is 9, 4 squared is 16. Go ahead and do it the old-fashioned way. 1 plus 4 plus 9 plus 16. You probably beat me to that. You get 30, right? Now use the formula. N is what? What's N? N is the top of the summation, the ending point of the summation. It's the last number. So it's 4. So use this formula. 4 times 5, n plus 1 is 5. 2n plus 1, well, 2n is 8, so that would be 9, right? 2 times 4 plus 1 is 9, and then divide that by 6, and this should give you the same number, which is 30. 4 times 5 is 20, 20 times 9 is 180, 180 divided by 6 is, in fact, 30. So this recipe gives you a quick way of adding up a bunch of perfect squares without actually having to add them. Okay, so let's add that to our list of tips here. Summation formula number 3. The sum of perfect squares is n plus 1, 2n plus 1 over 6. Okay. And then finally, the last thing we'll do before we actually use some of these formulas is we will say, generally, if you have a constant times an index, you can pull the constant out and then just do the formula for the index. So in other words, if you had a combination of the first one and the second one, you don't have to do the formulas twice. You could just remove the constant, put it out in front, and then do the formula for the index, and then that will give you the same result as the two formulas combined. Okay, which we've done that before, actually. The K is like your delta X, if you just want to know what the K is actually going to be when we're doing a real problem here. I mean, these are definitely real problems, but they don't have any context yet until I give you a function to work with. And then the same thing goes for the Ki squared. So if this was I squared, then you could still pull the K out and then do the I squared. Let's start with just this basic type, the Ki. So let's call this example 8. Let's go from I equals 1 to 20 of 3i plus 6. Now again, if you don't have these formulas, it doesn't mean that you can't get the right answer. You have a calculator, you could plug in 1, and then plug in 2, and then plug in 3. You could think of this as each one of these is a rectangle. Yeah, it's a rectangle with either a left or a right endpoint or maybe a midpoint. And you're going to add up the areas of all these rectangles. You can certainly do it that way. But I want to show you a much faster way. Because this is the way we're going to have to do it as we move forward. We distribute the summation just like you would do in algebra. Then for the ki, that's this one here, k is 3. You pull the 3 out to the front. And then you apply these formulas accordingly. Okay. All right, let's do it. So we got 3 times, or you could use a bracket. I like to use a bracket. That means the same thing as times. And then now the formula for I. So our n, oh, this one right here. The formula for I, the n is 20. So it's 20 times 21 divided by 2. And then for this one, the formula for a constant, I'm about to see. The formula for a constant, so this is like saying 6 plus 6 plus 6 plus 6 plus 6 20 times. Well, that's just 6 times 20. All right. I like to do as much of this as I can with mental math before I bust out the calculator. You can bust out the calculator now if you want, but a lot of this you can do with mental math. So 20 divided by 2 is 10. 3 times 10 is 30. So this becomes 30 times 21. I don't really feel like doing that in my head, 30 times 21. So that's the only one I'm going to use the calculator for. 6 times 20 is just 120. So I'm trying to minimalize the use of the calculator. So 30 times 21 is 630. And then plus 120. And then the final answer is 750. And I did that without really having to add very much. Notice I only added one time. Yeah. Instead of adding up 20 separate rectangles, this gives you a quick way of adding, which is really what math is about if you think about it. I mean, if we were happy, hundreds or even thousands of years ago with just adding everything up all the time, we could have done it, right? You could do it. You can get every answer simply by adding, right? I guess you might need some subtracting too, but then you could argue that subtracting is just another form of adding, right? But we invent these new techniques to simplify our lives. I don't want to add up 100 numbers or even 20 numbers. So you come up with a technique or a tip or a trick for making the result easier to obtain. That's the human condition. That's what we do, this all the time with everything. That's how we got from, walking to, riding on a horse, or from riding on a horse to riding on a wagon that was pulled by a horse, to driving a car, to flying a plane, etc., etc. All right, let's do the sum from 1 to 16, which really isn't too many, of 5i squared plus 7i. So this would be like adding up 16 rectangles. Okay, and then we're going to use this sort of version 2 of this fourth rule here, where if you have a ki squared, so there's your ki squared, you can again pull the k, the constant pulls out in front of the summation, and then you just apply the formula for the summation. And then we have another one of these, combination of k and I as well. So this will be the sum from I equals 1 to 16 of 5i squared plus the sum from I equals 1 to 16 of 7i We'll pull the constants out. Pull the other constant out. And then we will apply these two formulas. And I guess we don't need this one for this example. All right, we only need these two. Had there been a third term that was just a constant, then we would have used the other formula. All right, so I put 5. And again, you can put a dot, or you can put a bracket, or a parenthesis. I don't recommend using an X. All right, I squared. So you've got n. N is 16. So that's n. And then you got n plus 1, which is 17. And then you got 2n plus 1, which is 33. Yeah. 2 times 16 is 32, plus 1 is 33, divided by 6. Right. And then this one, you got, let me get rid of this line right here. You got 7, and then n, so n is 16, n plus 1 is 17, and then divided by 2. Now, if you want to bust out the calculator now, you can. I'm going to try to do a little bit of this ahead of time. So let's do, I don't know, let's see. Yeah, there's not much I can do here. Here, let's do this. Let's do 16 divided by 6. No, let's not do that. Let's go, I think I'm just going to break out the calculator. Yeah, let's just break out the calculator. I'm trying to like show off like try to do some mental math to clean this up. Really all you can do, here, you can do one thing. You can divide that by 2 and make that 8. And then you can divide that by 2 and make that 3. Right? So 6 divided by 2 is 3. 16 divided by 2 is 8. Again, if you don't want to do all this, just do it now on the calculator. I'm also going to divide 33 divided by 3 and make that 11. So now I've got 5 times 8 times 17 times 11. I'm trying to minimalize the use of the calculator. 5 times 8 times 17 times 11. I was this sort of, I don't know, unresolved childhood issue of being penalized for using the calculator. So I try to avoid it, unless it's absolutely necessary. All right, how about this one? 16 divided by 2, that's just going to be 8. All right, so now I only have to multiply 7 times 8 times 17. 7 times 8 times 17. So that's 952. And now I only have to add one pair of numbers, 952 plus 7480. And the answer is 8,432. There's another formula that's going to be saved for a future date. If we need it, it would be the I cubed formula. How to add up cubes, perfect cubes. We don't need it today, so I'll spare you. Let's go ahead and wrap this up with example 10. Let's get back to this. I got a blank graphing board here. It's been waiting for us. Let's get back to finding the area using Riemann sums, which is really the whole purpose of all of this. I have to erase these, so you'll keep them handy. I've got them written off screen here, so especially the one that's easy to screw up. So example 10. Estimate the area same thing as approximate, under the curve f of x equals x squared plus 2x plus 3 on the interval -2 to 4 with 12 rectangles, which is the most we've done so far. But once you see the technique, it could be 112. It could be 1,000. Really, the number of rectangles, if we do this example, thoroughly, should not matter. I want you to do it 3 ways. Using left, right, and midpoints. Yeah, so do all 3. Now, to keep track of it, of each method, we use different symbols. We'll say R12 is the right endpoint method. I'm going to do that one first. That's my favorite. L12 is the left endpoint method. Yeah, why 12? Well, because there are 12 rectangles. If it was 100 rectangles, then it would be R100 and L100. And then M12 is the midpoint method. So these are our notations for the 3 different methods for approximating the area under the curve. All right. Took up all my space here, so let's get rid of that. Let's move the function up here. We're going to need the function for every, well, not for every step, but for quite a few of the steps. I'm not going to draw the graph. Maybe I will very quickly, but not very detailed. And then I'm going to put over here n equals 12. All right, so let's start with R12. So R12 is the sum from I equals 1 to 12. My sigmas get a little sloppy there. From I equals 1 to 12 of delta x fxi. Yeah. Where delta x is b minus a. Be extra careful with the b's and the a's, and you're subtracting those, divided by n, which is 12. So that's 4 plus 2 divided by 12, which is 6 divided by 12, which is 1/2. Or you could say 0.5. It's up to you. I'll decide later which one I want to use. Sometimes I don't make up my mind. I just, whatever happens, happens. I try to avoid decimals when they're big, non-repeating, non-terminating, decimals, things like that. So either way is fine in this example. All right, so we got the delta x. Now let's see if we can remember the xi. Because we're doing right endpoints, the xi is very easy. It's a plus I delta x. So xi, a is -2 plus I times 1/2. Well, there's your delta x. Sometimes it's nice to put parentheses around the delta x. Or you could use a dot. Okay. You can also write it this way. And I think I will decide that that's better. I like that one. There's another way you could say I over 2. That would also be okay. At this point, I'm going to stop and say there's my xi. Okay. So now let's figure out our f. So let's take our f here. Now we have to do 12 rectangles. So I don't want to make a list of 12 numbers, right? I can just do it one time, just using xi. So f of xi is -2 plus 0.5i squared, right? It's x squared plus 2 times -2 plus 0.5i plus 3. That is all 12 rectangles written out with just one equation. You see, the I can be anything from 1 to 12. All right. Let's try to simplify this a little bit. So that'll be 4. Let's see, -2 times a half. What's -2 times a half? 1? -1? And then another -1, because you're doing it twice. You're squaring it. And then plus a half squared, which is a quarter, and then I squared. All right, that's a lot of algebra, but we're in chapter 4 now. So I'm going to put algebra, ALG. Study your algebra. You got to be good at that. All right. Now the rest of these are pretty easy. Just distribute. So you're going to get -4 and +1i, 2 times a half, and then plus 3. And then let's cancel the 4s. Let's cancel one of these i's. And so we have 0.25 I squared minus I plus 3. And you can't see that. Oh, can you squeeze that in there? I'm going to write it again up here at the top. So R12 is the sum from I equals 1 to 12 of 0.5, that's my delta x, times 0.25 I squared minus I plus 3. So I took the result of this fxi and I put it here. This is my fxi. And it required some basic algebra, distributing and multiplying and all of that. Okay. Now you might be saying to yourself, you know what, Dr. Jordan, I'm just going to make 12 rectangles and add them all up. And you certainly can, right? I won't know. However, on a test, that would take a lot of time. I know this is taking a lot of time too, but I'm talking my way through it. So, of course I talk a lot. That's what I get paid to do. All right. So I've got 0.5 times 0.25. So that's 0.125 I squared minus 0.5 I plus 0.5 times 3. I should know that. It's 1.5. The parentheses are not really required at this point. So now I've got to pull out the constant, multiply by the sum from 1 to 12 of I squared, pull out the next constant, multiply by the sum of I, and then the last one is just a constant. And there you go. And now we're going to use the recipes that we just learned, or that were just demonstrated. So you just use the top number here. That's your n. And then you do the formula for that particular n. So that's going to be 12 times 13 times 25. So that's n plus 1, 2n plus 1. 2 times 12 is 24 plus 1 is 25. Divided by 6. Minus 0.5 times, now this one's the easier one. It's just I, so that's 12 times 13 divided by 2. Plus, and then this is the constant rule, so it's just the constant 1.5 times 12. And now you do the calculator. I'm going to do a little bit of cleanup. Like I'm going to go 6 goes into 12 2 times. 2 goes into 12 6 times. Just to make my calculations a little easier. All right, so what do we got? We got 0.125, which is really just, what's that, an eighth? Yeah. If I would have kept fractions. Times 2 times 13. Oh, I hit something wrong. 0.125 times 2 times 13 times 25. So that's 81.25. That's this first one here. I've run out of space, so I'm coming up here. All right, the next one, 0.5 times 6 times 13. So that's 39. It's actually minus 39 because be careful here, there's a minus. So that's, when I said you're adding, you could be subtracting too, Just had a brain fart here. And then 1.5 times 12 is 18. And that's this last constant here. Just trying to think how we got the negative. Oh yeah, the negative. I forgot. The interval started at -2. I'm like, where did the negative come from? Because this is the first time we've actually seen a negative in the sum. I would be a little worried if the final answer came out negative because we haven't covered that yet. So I was starting to think, but it's because we started at -2. That's where this negative came from. All right. The final answer will not be negative. And so look how much adding we have to do. This is what the exchange rate was. I didn't want to add up 12 rectangles. So instead of adding 12 rectangles, I'm adding 3 numbers, or one of them is subtracting. So I've got 81.25 minus 39 plus 18. And so my approximation for the area for R12 is 60.25. And believe it or not, I've tried the same problem by actually adding 12 rectangles, and it takes like an hour. In fact, I think I even filmed it and decided not to show it to you because I didn't want to have you watch me add up 12 rectangles. So I have it on my computer. It's horrible to watch. And so this is a much more efficient way than actually adding up 12 rectangles. This is my favorite one, which is the right-hand one. The next two are a little bit laborious. I mean, if that wasn't laborious enough. Now, what's nice about it is you don't have to start all over again. You have your recipe here. So that's good. Okay. Let's go ahead and try to do it by salvaging some of the work that we've already done. So we have the sum from I equals 1 to 12. We're changing now to left hand. So we'll call this L12 now. I'm going to write this down just for reference at the end. It's off screen there so I don't lose it. All right. So my delta x is still 0.5. That doesn't change. Yeah. But the xi's are going to change. It's going to be a plus I minus 1 delta x. So the xi's are going to be negative 2 plus I minus 1 times 0.5. So that's going to be distribute the 0.5. You're going to get 0.5i minus 0.5. So you get negative 2.5 plus 0.5i. So those are your xi's for the left hand endpoints. It's very similar, just, you could think of the dot that used to be up here in the right-hand corner get shifted to the left, and so now it's here. Yeah, so this is the new location, and that's kind of, I hope, intuitive, because each one of these rectangles was 0.5. So look, you see that minus 0.5? So minus 0.5 shifted the dot from the right corner over to the left corner, and this is your new formula. Right? So if you really have a good intuitive sense of the geometry of what's going on, when I say find the left, if you've already done the right, you can just go right to here and then shift it to the left, and there's your new formula. And you can skip a lot of these steps. I'm always afraid if I do that, I'll lose too many people, So I always assume that a full walkthrough is better than a half walkthrough. I do want to give you more space this time, though, so I'm going to go ahead and copy this answer here so I can reclaim my territory. Negative 2.5 plus 0.5i. All right, so now we do the f of xi. So that's going to be, I better give myself some more space. F of xi is negative 2.5 plus 0.5i squared plus 2 times negative 2.5 plus 0.5i plus 3. So you're just taking this function f and putting, in place of the x's, you're putting your xi's, which go inside of the variable position. Practice your algebra. If you have to use a calculator to help you, 2.5 squared is 6.25. It's a negative squared, so it's going to be positive. 2.5 times 0.5 is 1.25. But then you have to do it again, so you get a negative 1.25. So you're going to always have, when you square a binomial, you always get two copies of the same term in the middle. And then 0.5 squared, you already know that. It's 0.25 I squared. So again, all of this comes from this algebra review. Right? Just reviewing your algebra. The rest of it's pretty straightforward. 2 times negative 2.5, that'll be negative 5. 2 times a half is 1. So that's 1i. And then plus 3. Okay. So now what do we got? We don't get as much canceling as we got before. Let's just put the square term first, 0.25 I squared. Here, let's cross them off as we go. Let's do our i's. So that's negative 1.5, 1.25, negative 1.25, and then plus 1. If you have to use the calculator, you can. That's negative 2.5 plus 1. Which is negative 1.5. All right, we'll cross those off. And then we've got 6.25. I'm just going to use the calculator for this. 6.25 minus 5 plus 3 is plus 4.25. So this is your fxi, which goes here. And again, if you're thinking, well, you know what? I would rather just add up 12 rectangles. Well, then you certainly have the ability to do that. However, what if it's 20 or 50 or 100? Right? At some point, it starts to get where adding the rectangles is not very fast. Now, sure, if it was 4, I mean, I admit, if this was 4 rectangles, I probably would not be doing this. I would just add 4 rectangles. But my general limit is about 8, maybe 10, 8 or 10. You know, I mean, count on your fingers. If it's more than I can count on 2 hands, then I'm just going to use some better method. All right. So we're doing L12. So we have the sum L12 is the sum from I equals 1 to 12. Delta x was 0.5. And then fxi is what we just worked on. So 0.25 I squared minus 1.5 I plus 4.25. And I don't need any of this anymore. So that's the sum from I equals 1 to 12. Go ahead and distribute that. It's funny because I'm going to distribute it, and then in the next step, I'm going to pull it out anyway. But I just want to get rid of, or at least combine some of these decimals. So 0.25 times 0.5. Hey, look, it's the same as last time, 0.125. So we might have, you know, if you've already got that one written down from the last one, it's the same. Let's see, 0.5 times 1.5. Oh, that's 0.75 I. And then 0.5 times 4.25 is 2.125. Let's skip one step. We're going to pull out these constants anyway, so I might as well just do that now. And then we're going to apply the I squared formula. So that's 12. It's the same as it was last time. 12, 13, 25, all over 6. Should be the same as last time. Yeah. That first term doesn't change. These terms will be slightly different. So 0.75 times 12 times 13 divided by 2. And then for the last one, it's going to be 12 times 2.125. Let me try to make that look a little nicer. I don't know if that helps, but we're going to put it in my calculator anyway. So, all right. Clean it up just a little bit. So 6 goes into 12 2 times. 2 goes into 12 6 times. And then here comes the calculator. So I've got 0.125 times 2 times 13 times 25. So this one is 81.25. Hey, that's the same number it was last time. Yeah. It's these last two terms that change. So let's do the next one. 0.75 times 6 times 13, 58.5. And then the last term, 12 times 2.125 is 25.5. All right. And then the final answer. Just add these numbers up on your calculator. So 25.5 minus 58.5 plus 81.25. 48.25. Quite different. Yeah. All right, so the last approximation is M12, the midpoint approximation. We still have delta X is the same, 0.5. For the midpoint rule, when we find our xi's, we're looking for the midpoint. So it's going to be a plus 2i minus 1 over 2 times delta x. I erased it, but our a was negative 2. It's the same as it was in all the others. And our delta x is 0.5. Now remember, I have to take this and plug it into the function. So let's clean it up a little bit, make it a little bit easier to plug in. So we'll distribute the 0.5, and then we'll divide by 2. So that'll be 2 times 0.5, which is 1. Yeah, 1i, and then divided by 2. And then minus 0.5 times 1, which is 0.5, divided by 2. And that gets rid of the parentheses. And then now we'll divide these by 2. So we get another 0.5i. Yeah, 1/2. And then 0.5 divided by 2 is negative 0.5 divided by 2 is negative 0.25. And then we'll combine these constant terms. Negative 2.25 plus 0.5i. So that is our xi that we will plug in to our function to get the top of the rectangles. Now, intuitively, again, if you have a good understanding of the graph and you're thinking, well, I'm looking for the midpoint, right? It kind of makes sense. how it got shifted to the middle of the interval, because each interval is half, 0.5, that's your delta x, and then you're shifting it over to the middle. So this point here, xi, is in the middle between negative 2.25 and then shifted over to the right another delta x. Okay, but with or without the graph, you can still see that you have the same value. So now we're going to take these numbers and plug them in. So let's copy them up here. Negative 2.25 plus 0.5i, just so I can have this board space back. And then we'll do our f's, f of xi. So here's our function. So we have x squared, which will be negative 2.25 plus 0.5i squared. So that's your x squared. Plus 2 times x, and again, xi. So negative 2.25 plus 0.5i, and then plus 3. And again, there's a lot of algebra here that you need to review. Or do it all step by step. I've done this several times. So I've got 2.25, negative 2.25 squared. Use a calculator if necessary. So negative 2.25 squared is 5.0625. And then you have negative 2.25 times 0.5, which is negative 1.125i. But remember, you're multiplying this by itself twice, so you're going to have another copy of that. You don't have to do it twice. You'll get 2 copies of the same factor. And then finally, you got the 0.5 times 0.5, which is another 0.25 I squared. So this represents all of this squared out. Again, more algebra review. All right, it's good for you. And then the rest of these, again, are pretty straightforward. So you're going to go 2 times negative 2.25, which will be negative 4.5. I'm just going to put it underneath here because that will cancel. Or not cancel, but combine. And then I've got 2 times 0.5, so that's positive 1i. 2 times 0.5. And then I still have the plus 3. I guess I'll put the plus 3 over here. So all of my constants will combine together. I like to put this in descending order. So let's put the I squared term first. Sometimes I do that earlier in the process, but I guess I've been waiting till the end. And then that one's gone. And then I like to do all my middle terms. So I've got 1.125. They're both negative. So that's negative 2.25 when you combine these, plus 1. That's negative 1.25i. So those are all gone. And then I put my constant terms last. I don't want to screw this up, so I'm just going to do it all in the calculator. 5.0625 minus 4.5 plus 3. So plus 3.5625. So this is your fxi. Those are your function values, the roofs, the ceilings of the function for each of the indices I. All right, so then all of this goes into here. And so our midpoint summation formula is the sum from I equals 1 to 12. Delta x is still 0.5 times this function fxi 0.25I squared minus 1.25I plus 3.5625. And that is what we're actually going to add up. Before we do any adding, let's simplify it a little bit more. From 1 to 12, we'll distribute the 0.5s. Got a lot of decimals here, so 0.5 times 0.25. We could have done this whole thing with fractions. I don't know if that would have made it any easier, but you know, it was possible. So that's 0.125I squared. Then I got 0.5 times 1.25, so 0.5 times 1.25. Again, it's negative 0.625I. And then plus 3.5625 times 0.5, 1.78125. Yikes. Maybe fractions would have been easier. But we're already halfway through it, or more than halfway through it with just decimals. And now here's where those formulas come in, those tips and tricks for adding up these rectangles. Instead of actually adding up 12 rectangles, I can use the formulas, pull out the constant, then multiply by the recipe for I squared, which you have hopefully written down. It's the same as it was last time. It's 12 times 13 times 25 all over 6. That's your I squared formula. And then you pull out the 0.625 and you apply the I formula. That was the easier one. That's 12 times 13 over 2. And then the formula for a constant, just multiply the top index, or the number of rectangles, which is 12, times whatever that is, 1.78125. And if you want to just put this all into your calculator now, you can. But as I've been doing this whole time, clean it up just a little bit. 6 goes into 12 twice, and 2 goes into 12 6 times. And now at least I don't have any division to do. I've done it all ahead of time, and now I just multiply. So I've got 0.125 times 2 times 13 times 25. Now that looks familiar. 81.25. For the next one, I've got 0.625 times 6 times 13. That's 48.75. And then plus the last term, 1.78125 times 12 is 21.375. And so instead of adding 12 rectangles, I just add up these three values, and that will give me my final result. So let's go through that. 21.375 minus 48.75 plus 81.25, and we get 53.875. And that is our midpoint approximation. Whew. Well, we got through it. We have 3 different approximations. Had I spent, an hour drawing the graph, it would, be a parabola. We would have all the different rectangles underneath the parabola. There would be 12 rectangles. I'm not really being very detailed. And then based on where we put the endpoint, whether it's left, right, or middle, would give us the 3 different values. I did save all my answers, so we can do the summary of the results, just so you can have them all in one screen. The right endpoint with 12 rectangles, the area was approximately 60.25. The left endpoint with 12 rectangles came out to 48.25. And even though I did the midpoint one last, oh, why did I just erase it? Oh, I have it on my screen. Oh, good thing I kept my calculator. The midpoint one is generally in between the two, which should make some sense, right? You've got the right endpoint was an overestimate. The left endpoint this time came out to be an underestimate. And then the midpoint is kind of right down the middle. So even though I wrote them in this order, sometimes it's easier to put the midpoint one right in the middle, and then you see that there's some sort of a pattern to this. So that is it for the Riemann sums and the approximations. In my next video, we will continue with this summation formulas. We'll introduce some more calculus techniques, and that'll be the definite integral coming next. But until then, I'm Dr. Jordan. I'll see you on the internet.